Bismillahirrahmanirrahim. Assalamu alaikum. Today I welcome you in the lecture series of digital filter design. And today's our topic is ideal filter. How can we implement the ideal filter? That's we are going to do today in MATLAB. So let's start the lecture. What is ideal filter? First of all, we need to know an ideal filter has a magnitude response equal to 1 in the pass band and 0 in the stop band and has a zero phase everywhere. That is basically the requirement of the ideal filter. We want to pass a frequency of interest without any distortion and block other frequency component. That is what we want, and we don't want any phase distortion in the pass band. So to develop a stable and realizable transfer function, the ideal frequency response specify relax including the transition band between the, that is basically the implementation point of view. But one thing is very much important regarding the ideal filter are not practically realizable because they have unstable and non-causal impulse response. Why they have impulse? Let's see the uh, these are the four basic famous ideal low pass filters: ideal high pass filter, and band pass filter, and band stop filter. In ideal low pass filter, the magnitude response is from 0 to omega c, and omega c to pi is 0. And same for the high pass filter, 0 from 0 to omega c and omega c to pi. And in band stop filter, we omega c to omega c, that it is 1, and otherwise it is 0. And same for the band stop filter, 0 to omega c1 is 1, and omega c2 omega c1 to omega c2 it is 0. And these are the range of pass bands from 0 to omega c. I already told you in the last slide. Okay, we are going to implement ideal low pass filter, and why it is not able to design practically. Let's take a frequency response. H of e j omega is a low pass filter. Frequency response is 1 from 0 to omega c and 0 from omega c to pi. That is basically the graphical magnitude response of ideal low pass filter is from 0 to omega c it is 1, and omega c to pi it is 0. If we want to see it is why it is unstable and non-causal, we want to calculate the its impulse response. To calculate the impulse response, we need to apply the inverse discrete time Fourier transform on the frequency response. So that is the for our frequency magnitude response, and that is the formula of inverse discrete time Fourier transform, IDTFT. 1 from 1 to 2 1 over 2 pi. Let me have a pointer. 1 over 2 pi integral minus pi to pi. We have a function that is 1 from omega c to omega c, though we can change the limit from minus omega c to omega c instead of minus pi to pi. H of e j omega, that is 1 in that range, and e j omega n, and we don't need to integrate further because otherwise the function is 0. So if we take integral 1 over 2 pi upper limit minus e j omega n c over j omega, if apply the limits, upper limit minus omega c minus e minus j omega c minus lower limit. If we simplify this equation, we have sine n omega c over n pi. That is basically our impulse response. If we see, this impulse response is non-zero from minus infinity to infinity, so that is a non-causal impulse response. A causal impulse response must be zero for the negative time indexes, but this impulse response is non-zero for negative time indexes, so that's why it is a non-causal filter. And also this impulse response exists from minus infinity to infinity. It means this impulse response is also unstable impulse response. So what we do, instead of having a zero phase magnitude response, we try to relax the condition of phase response and introduce a linear phase. Instead of 1, we have ej omega d. That's we try to do for which has a linear phase response and omega is equal to 0 from 0 to pi. The magnitude response will remain same 1, and the phase response is theta of omega is equal to minus omega d. If we take the derivative, and that is basically tau of omega is basically group delay. That is basically negative gradient of phase response. A phase response is minus omega d, and if we take the derivative with respect to omega, then we have only d, that is the group delay of this linear phase filter. Okay, that is basically an ideal filter with the linear phase. Only change here we have, instead of 1 we ej minus omega naught and naught, and from 0 to omega c to pi, that is 0. Here the magnitude response, and we have now what is, we introduce the phase, linear phase from minus omega to c to omega c. Now we want to see, is that impulse response is again stable or no, or causal. So if we take the inverse discrete time Fourier transform, the impulse response will remain same, sine omega c n minus n naught and over pi n minus n naught, but only the shift, otherwise it will remain exist from minus infinity to infinity. Duration is also infinite length, so this is again infinite length, unstable and non-causal impulse response. If we want to implement, we just need to do is to truncate and shift and truncate the impulse response. That is what we can do only to implement digitally by truncating the impulse response for the finite number of terms. A realizable FIR approximation to the ideal low-pass filter can be developed. Truncation approximation may or may not be exhibit linear phase depending on the value of the n naught chosen. Okay, if we choose n naught n by 2 with the n positive integer, the truncation of shift approximation can be this, where n naught is n by 2 and the limit truncation from 0 to n naught. It is because to maintain the linear phase and symmetry of the impulse response. If our impulse response is symmetrical, the impulse response will remain same. That is basically how can we do. We only shift by n naught by 2. For this case, n by 2 is 6, and we truncate the impulse response from 0 to 12. That will remain symmetrical impulse response, and it exhibit linear phase. Now let's try to implement this on the MATLAB. Let's open our MATLAB. Let me open my MATLAB. Okay, now here we have now that is our MATLAB screen. I am going to implement line space from -5 to 5, that create 5 to 5. This give me a line vector, a line. Comma, y is equal to sin t And now plot t comma y, that is the plot of the sync function. So this is our plot of sync function. Now that is actually we have a value from, but actually uh, these values store in y uh, variable and from 0 to 100, because in MATLAB we don't have any uh, minus index. If we simply plot y, we can see this whole signal exists from 0 to 100, so we don't need to give any shift to move on the positive time indexes. It is already stored in the positive time indexes. So what we need to do, just calculate the impulse response. I simply open figure 2 and let's have a response, my underscore response or of y, and we have magnitude response, phase response, and the pole zero plot of this. So if I want to implement to improve this, just need to improve the number of points, comma. If I want to improve the point, again this and my response, and let's suppose plot figure 1, plot y, and that is our plot, and here is the impulse response, that is in the figure 2. So you can see the improved in magnitude response. So that is how can we implement ideal low pass filter in MATLAB using truncation and shifting our frequency response. So hope you people like my lecture. If you have any comments, you can ask me in the description in comment section, and kindly share and subscribe my channel. See you next time. Allah Hafiz.